Today consider the topic aldehyde and ketones. What are aldehyde and ketones? The carbonyl group is present in aldehydes, ketones, and carboxylic acid and their derivatives as well as in carbohydrate. It is one of the most important functional groups in organic chemistry. Its chemical properties are straightforward, and understanding of its characteristic reaction patterns leads very quickly to an understanding of a wide variety of organic and biochemical reactions. The functional group of an aldehyde is a carbonyl group bonded to a hydrogen atom. Hydrogen atom. In methanol, the simplest aldehyde carbonyl group is bonded to two hydrogen atoms. Methanol to two hydrogen atoms. In other aldehydes, it is bonded to one hydrogen atom and one carbon atom. The functional group of a ketone is a carbonyl group bonded to two carbon atoms. Two carbon atoms, for example. Acetone is the simplest ketone. Acetone nomenclature name propanone. Because aldehydes always contain at least one hydrogen bonded to the CO group, they are often write RCO, RCO, RCO. Similarly, ketones are often write RRCO. How do we name aldehydes and ketones? The EUPAC names for aldehyde and ketones follow the familiar pattern of selecting as the parent alkane the longest chain of carbon atoms that contains the functional group. To name an aldehyde, we change the suffix "e" of the parent alkane to "al", because the carbonyl group of an aldehyde can appear only at the end of a parent chain, and numbering must start with it as carbon 1. There is no need to use a number to locate the aldehyde group. For unsaturated aldehydes, we show the presence of the carbon-carbon double bond and the aldehyde by changing the ending of the parent alkane from "-n" to "-enal" and "-in" to show the carbon-carbon double bond and "-al" to show the aldehyde. We show the location of the carbon double bond by the number of its first carbon. First carbon, please. Name hexanal, 3-methylbutanol, and 2-propanol. Position P bond 2. In the UPAC system, we name ketones by selecting as the parent alkane the longest chain that contain the carbonyl group and then indicating the presence of this group by changing the E of the parent alkane to 1, suffix 1. The parent chain is numbered from the direction that gives the smaller number to the carbonyl group. Small the number, it's correct. Small the number. While the systematic name of the simplest ketone is 2-propanone. 2-propanone, position carbonyl group 2. The UPAC retains its common name acetone. For example, 5-methyl, position radicals 5, 5-methyl 3-hexanone. Next, lowest number carbonyl group, 2-methyl, 2 position, 2-methyl cyclohexane suffix on. Aldehydes often named for the acid they convert to during oxidation. Uh, for example, formic aldehyde, formaldehyde. Next, ethanol, acetaldehyde. Um, Next, propionic aldehyde, 3 carbon containing. Butyric aldehyde, butyral aldehyde. Next compound, isomer version, isobutyric aldehyde. And Valerian aldehyde. Next, Valerian aldehyde. Okay, next. Ketones are often named after hydrocarbon radicals attached to the carbonyl group. For example, dimethyl ketone, acetone. One radical, two radical, radical equilibrium. Next, methyl, ethyl, name compound, methyl-ethyl ketone. Methyl isobutyl ketone, methyl, radicals isobutyl, branched chain, isobutyl. Diisopropyl ketone, isopropyl radical and isopropyl radical. In naming aldehydes or ketones that also contain an OH or NH2 group elsewhere, and the molecule the parent chain is numbered to give the carbonyl group the lower name number. NH substituent is indicated by hydroxy and an NH2 substituent is indicated by amino. Hydroxy and amino substituents are numbered and alphabetized along with any other substituents that may be present. Trivial names are acceptable. Uh, Formaldehyde, acetaldehyde, acetone, acrolein, phenacrolene. Formaldehyde, acetaldehyde, temperature boiling point 21 Celsius degree. Acrolein gases with not very pleasant smell. Lower aldehydes and ketones liquids. Soluble in water decreases with an increase in the number of carbon atoms. Higher solid matter. Smell of many ketones when diluted too much fruity flavor. The melting and boiling point of aldehydes and ketones is higher than those of hydrocarbons with the same number of atoms, but lower than that of alcohol, due to lack of intermolecular hydrogen bonds with each other. What are characteristic reactions of aldehydes and ketones? Aldehydes are oxidized to carboxylic acid by a variety of oxidizing agents including potassium dichromate, uh, hexanal oxidation form compound hexanoic acid. Aldehydes are also oxidized to carboxylic acid by the oxygen in the air. In fact, aldehydes that are liquid at room temperature are so sensitive to oxidation that they must be protected from contact with air during storage. Often this is done by sealing the aldehyde in a container under an atmosphere of nitrogen. Ketones, in contrast, resist oxidation by most oxidizing agents, including potassium dichromate and molecular oxygen. The fact that aldehydes are so easy to oxidize and ketones are not allow us to use simple chemistry tests to distinguish between these type of compounds. Suppose that we have a compound we know is 80 and aldehyde or a ketone. To determine which it is, we can treat the compound with a mild oxidizing agent. If it can be oxidized, it is an aldehyde. Otherwise, it is a ketone. One reagent that has been used for this purpose is a tolerance reagent. Tolerance reagent is prepared from silver nitrate and ammonia in water. When these two compounds are mixed, silver ion combines with NH3 to form the complex ion argentum NH3 2. When this solution is added to an aldehyde, the aldehyde acts as a reducing agent and reduce the complexate silver ion to silver metal. If this reaction is carried out properly, the silver metal precipitates as a smooth mirror-like deposit on the inner surface of the reaction vessel, leading to the name silver mirror test. In the remaining solution is acidified with HCl, the carboxylic ion RCO-, formed during the aldehyde's oxidation and converted to the carboxylic acid RCOOH. Today, silver one is rarely used for the oxidation of aldehydes because of its heat cost and because of the availability of other more convenient methods for this oxidation. This reaction, however, is still used for making silver mirrors. Okay, next reaction, reduction. We saw that the C-C double bond of an alkene can be reduced by hydrogen in the presence of transition metal catalyzed to C-C single bond. The same is true of the CO double bond of an aldehyde or ketone. Aldehydes are reduced to primary alcohol, and ketones are reduced to secondary alcohol. For example, pentanol react with hydrogen transmission metal catalyzed form 1-pentanol, primary alcohol. Next reaction, cyclopentanone react with hydrogen transmission metal catalyzed cyclopentanol, secondary alcohol. Next reaction, and advent of the two hydrogens added to the carbonyl group in this reduction on comes from the reducing agents, and the other comes from aqueous acid. Reduction of cyclohexanone, for example, with this reagent gives cyclohexanol. For example, cyclohexanol reduced form cyclohexanone reduced from cyclohexanol. An advantage of using tetrahydrogen borate sodium over H2 metal reduction is that tetrahydrogen borate sodium does not reduce carbon-carbon double bonds. Not reduced. The reason for this selectivity is quite straightforward. There is no polarity, no partial positive or negative charge on a carbon-carbon double bond. Therefore, C double bond has no partially positive side to attract the negatively charged hydrogen. In the following example, tetrahydroborate sodium selectivity reduced the aldehyde to a primary alcohol. In biological systems, the agent for the reduction of aldehyde and ketones is the reduced form of the coenzyme nicotinamide dinucleotide, abbreviated NADH. This reducing agent, like tetrahydroborate sodium, delivers a hydrogen to the carbonyl group of the aldehyde or ketone. Reduction of pyruvate, for example, NADH, gives lactate. Next reaction, addition of alcohols. Addition of a molecule of alcohol to the carbonyl group of an aldehyde or ketone forms hemiacetal, half-acetal. The functional group of hemiacetal is a carbon bonded to the OH group and one or R group. In forming a hemiacetal, the hydrogen of the alcohol adds to the carbonyl oxygen and OR group of the alcohol adds to the carbonyl carbon. Show here the hemiacetal. Show here the hemiacetal formed by addition of one molecule of ethanol to benzaldehyde and cyclohexanone. Benzaldehyde addition ethanol, one molecule, form hemiacetal. Next, cyclohexanone react with ethanol, form hemiacetal. Hemiacetal are generally unstable and are only minor components of an equilibrium mixture, except in one very important type of molecule, when a hydroxyl group is part of the some molecule that contain the carbonyl group and a 5 or 6-membered ring can form. The compound exists almost entirely in a cyclic hemiacetal form. In this case, the OH group adds to the CO group of the same molecule. We will have much more to say about cyclic hemiacetal when they consider the chemistry of carbohydrate. Chemistry of carbohydrates. Uh, Hemiacetal can react fuse with alcohols to form acetals plus water. This reaction is acid catalyzed. The functional group of an acetal is a carbon bonded to two R groups. For example, hemiacetal ethanol react with 2 mol ethanol form acetal, and hemiacetal plus ethanol form acetal. All step in hemiacetal and acetal formation are reversible. As with any other equilibrium, we can make this on go is 80 direction by using Le Chatler principle. If we want to drive it to the right formation of the acetal, we either use a large axis of alcohol or remove water from the equilibrium mixture. What is keto-enol tautomerism? A carbon atom advanced to a carbonyl group is called an alpha carbon, and alpha hydrogen atom bonded to it is called an alpha hydrogen. Alpha station, alpha hydrogen, alpha carbon. Position 1, position 1. Mm, carbonyl compound that has a hydrogen on alpha carbon is in equilibrium with a constitutional isomer called an enol. The name enol is derived from the UPAC designation of it has both an alkene and an alcohol. All keto and enol form are examples of tautomers constitutional isomers. Constitutional isomers. In equilibrium with each other that differ in the location of hydrogen atom and double bond. This type of isomerism is called keto-enol tautomerism for any pair of keto-enol tautomers. The keto form generally predominate at equilibrium. Aldol-Carton condensation. Condensation is a reaction that accompanied by the formation of a low molecular weight product water. For example, carbonyl component containing carbonyl group, methylene component alpha position hydrogen. In presence alkali, form aldol, no stable compound, and for temperature minus water, form product croton. Next slide. A reaction involving the stage of nucleophilic addition at carbonyl group and nucleophiles. For example, acetaldehyde react with NH3 ammonia form salt. No stable compound minus water form amino A There is trimerization form heterocyclic compounds. Marline plus 25% ammonia. For example, methanol react with ammoniac, form hexamethylene tetramine urotropine. Anti-influenza Caltex, uh, calcium Cl2 currently not applied. Corrosion inhibitor, phenol formaldehyde resins. Uh, Urotropine react with acid nitrate, forms hexogen. Ketones do not form ketamines. They react slowly with ammonia through the self-condensation stage. For example, acetone in presence alkali form active alkylidine derivatives and react with ammoniac form amino ketones. Next reaction, substitution reaction at the alpha position to the carbonyl group. Collagenation in an acidic environment. In an alkaline environment. With an excess of halogen, all can be replaced hydrogen atoms. Galliform cleavage, galliform reaction. Chlorination plus oxidation of ethanol with chlorine chloral. Chloroform when treated with alkali. Discovered in 1822, think 1870. The iodoform reaction. Qualitative test for grouping acetyl group. Acetyl group. In a solid ampoule, galliform iodine. Thank you for attention.